algebras, for which you do have interesting difference equations and lots of stuff for experimental math, I'm sure. So we're eager to hear Tom speak about recurrences.
First, I want to say something about video. Going to sort of jump in, and then I'll stop and go back and make sure got everybody up to speed. So let's say that I think of these as being unit distances right up coming out of the board. I'll just label these 3 unit lines A, B, and C. And then I will also see what I want. That one. So that's then A, C, B. So if they're parallel, they get the same. You know, B. B, C, A. That. C, B. Take those, just 4. So 4 different triples. So here are the 4 triples: A, B, C, A, C, B, B, C, A, and C, B. Now I'm going to look straight down along the vector 1, 1, 1. So from here, right down to the origin. Right, I want to draw this. Should look like a hexagon. And I'll just read off the labels out. So I've got A, B, C. Second term, BCA should be up there, that's this one. And CBA should be there, that's this one. So that's the view that you would get from straight down. Now,
so it's a cube, and if you project it, you get a hexagon?
Yeah. Yeah, when you take the homogeneous slice to the interlattice, you get the triangular lattice. And alright, so this is all just completely formal. These are just symbols that are allowing us up to formally multiply by each other here. So now if I stick with weak permute, just by moving this axis up and around, then this guy's going to come here, and come here, and back to here. And so since I put a plus sign there, I'm going to get a plus, plus, plus. Minus sign there, minus, 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 so they'll cancel. And same thing with these guys. This can go here, and there's going to get plus, 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 and minus, minus, minus. So they will all cancel out. If I take cyclic permutations of this, so I need a negative on my ACB, and a negative on my C. A negative on my BCA. So down here, plus cyclic. Which means that A goes to B, goes to C, goes back to A. That equals 0. Okay, now this is a commutator, formal commutator. I've got A in the front here, so I've got A commutator A in the front here and the back here, so A commutator BC. So I just add those up. And then the other one here should be minus A CB. So now I've got A, B, C.
Right. Does it favor Jacobi?
This is the famous Jacobi.
Yeah. It's a nice motivation.
Right, so I just need to be able to multiply these things. I need things to be associated. So you take any associative algebra, and you do this, plus cyclic, zero. Okay, so any associative algebra with commutators, so the algebra as we say. So this is the Jacobi identity. There's also skew symmetry, and I use almost the same way, it's just something like that. The one that is a plus, one that is a minus, and you just reflect them. So there's also skew symmetry, so AB equals negative. Okay, so a Lie algebra is something that satisfies this guy, and something that's you need vector space that has multiplication that satisfies these. Once told that every math problem should have a proof by a senior mathematician. So here's my nature. I have one proof. I prove that every associative algebra is not. And now I'm going to jump into the vertex algebras. Except first, I need to do some preliminaries. This Jacobi identity is related to the Jacobi identity I'm going to talk about later. That's why I wanted to put it up. So. So in order to even state anything formal algebraic, the way through any, we do a little bit of preliminary form kind. And so, first of all, if I have a derivation of an algebra, so let A be an algebra, capital D derivation. So d of AB equals d of A B plus A dB. That's all that means. And then d to the n B, I keep calling out, that's just the binomial formula, right? So n factorial d to the k A over k factorial d to the L B L factorial k plus L. And then I'll divide both sides by n factorial. Sum. Infinity. That side looks like E to the D B. And this side looks like E to the D A D and B. So that's a version of the binomial formula. And this version is called the automorphism. It's automorphism property version of the binomial formula. Okay, so for me, the algebra isn't really going to be an algebra, but it's going to be close enough. So it has a partial multiplication. You have to check that some things are well defined. And the capital D is going to be d dx, so e to the y d dx. But of course, I'm defining it in terms of the series. Right, so this is defined to be the sum y dn d dx dn n factorial. And I'll let f of x, g of x be the Laurent series. Denote it this. can be a series of powers of x, non-truncated in both directions, and the coefficients are just coming from some vector space. And obviously I'm going to want to be able to multiply them, so sometimes this vector space is going to be a space, vector space of endomorphisms of some vector space. So then e to the y d dx, g f of x, g of x, that should be e to the y d dx, f of x times e to the y d dx, g of x, whenever both sides are well defined. So these, maybe I can't always multiply them. So I'll give an example where I can't multiply them. Delta function is defined to be the sum of x to the n over all integers. So delta x times delta x is not well defined. So I can't have those both be f and g. And the reason is that if I try to do this and I try to check the coefficient, I'm going to have an infinite number of terms contributing to every coefficient, and that's the thing I have to make sure doesn't happen. So it has to be finite summability of every term. And as long as you got that, then this works. Sort of unorthodox definition. So definition here, x plus y to the n. So e to the y d dx, x to the n, and is any integer. And so that should, of course, be equal to what we want it to be equal to when n is positive. So I'll check that. So for n is 1, it's easy to check. These terms go away to 0 except first and second, you get x plus y. So x plus y again. The 1, excuse me, is x plus y. And now I want to check that x plus y to the n times x plus y to the n is x plus y to the n plus n for n and integers. I'll use that automorphism property. So how is this defined? This is e to the y d dx of x to the n, e to the y d dx of x to the n, automorphism property, e to the y d dx of x to the m plus n. This is simple. So all of our arithmetic is going to be what we want. And it's a little bit funny though when m is a negative integer. You will notice that this is definitely not symmetric in x and y. Here, the powers, if that's a negative number, are going to go negative. As that derivative keeps pushing it down. If the powers of y are always going to be strictly non-negative. Okay, so it's asymmetric in the two. So it is symmetric if n is non-negative, and it's completely asymmetric as soon as n is negative.
So 1 of x plus y is not the same thing as 1 over 1 plus x.
Right. And so the convention is the guy that wants to go up here, I'm always going to write in the second position. We'll call that the binomial expansion. Yeah.
So, oh, never mind. Where the x's are some sort of vector space, but then when we get this other addition and we add y, that addition isn't necessarily commutative?
Oh, this thing?
Yeah.
This particular use of addition is not commutative. Whenever I write this symbol, I have to treat it as an atomic symbol, and I have to always interpret it as this.
But something like, if you had such a symbol and there was an x squared plus x floating around, those x squareds and x's would commute?
Wait, x squared.
Like x squared plus x plus y. Does that equal, can we switch the x's? X plus x squared?
Yeah, here everything is fine. It's just a polynomial. If I wrote that, then this you don't want to try to break up in any kind of funny way.
Okay, sure.
But it's
How about if we do that whole thing, x squared plus x plus y, all that jazz to the -1? Yeah, you can take away that
defined.
-1 in the middle there.
So this question mark, check that it's well defined.
1 over x plus x is equal to 1 over x plus x, right?
That's not good enough.
If y is equal to x, then it's... Right, exactly. Yeah.
It's all right.
Okay, next time it happens, give a donation to the OEIS Foundation, $20. Okay? That's like next time. Yeah, $20.
I'll go back to that delta function. The delta function is really trying to play a key role in everything here. So x times delta x equals 1 times x. Because it just shifts everything over and lands back on itself. That's basically why it's called the delta function. It's some kind of formal shift from its actual delta function distribution. Or in other words, x minus 1 of delta x. 0. Similarly, delta of x over y, if I multiply that by x, it should be equal to 1 over y to the negative 1 delta of x, y. For here, now I've got x to the 10 over y to the 10, they always match. Here I shift the top one forward 1, and here I pull the bottom one backwards 1, so they're the same. So this is equivalent to x minus y. It's delta of x over y.
Can you just go through that step one more time if you're out? Yeah.
So a term here would go from like x to the 10 over y to the 10 would go to x to the 11 over y to the 10.
Okay.
And then here, x to the 11 over y to the 11 is going to go to x to the 11 over y to the 10. So on the top I push forward, and it's always going to be 1 shifted forward from here, and down here also it's always going to be 1 shifted forward from here. Now, since I've got x, that's nice, so I get to use that. So x plus y is delta of x plus y z. That's going to shift the power on the top forward 1. 1 over z to the negative 1 delta of x plus y. So that's just a z. Combine them, I get the x plus y. Minus z. That's delta of x plus y over z. So there's the top minus bottom. Right. X minus y. Or here, x plus y minus z. That polynomial annihilates this delta function.
So you cannot immediately go from here to here. You have to, you can't just naively replace x by x plus y and y with z. This is
from here to here, I just need this, and I need to make sure things are well
yeah,
defined.
you justify this thing.
But there, it's easy to see this one's well defined because every. So first of all, without this, I just had delta x plus y over z. Every power of z picks up exactly 1 term of x plus y to the negative, whatever, and so that's well defined. And since that just shifts, you can check pretty easily if this is well defined. And this is also going to be well defined because that's just a polynomial. Actually, whenever you have a polynomial, it doesn't mess up well definedness.
Okay, so I don't mean to
No, no,
slow you down. When we have this x plus y inside that delta,
yeah.
that is not the same as having like a y plus x inside the
Okay,
delta,
so,
right?
yeah, so how's this defined? Delta x plus y over z is equal to e to the y e dx delta x over z. And that's well defined, and that's a well defined operator. You just every y, you take the right derivative and apply it to there. Oh, actually, I should have written that before. The automorphism property. So e to the y dx of f of x. That's going to be equal to f of x plus y. So that's also true. That's also true. It's it follows from the automorphism property in my definition here.
Okay.
Or alternatively, I could just have it expanded out, so this would be the sum of x plus y to the n over z. All right, so the fact that this polynomial annihilates this means that if I look at the coefficients of this, I've got a difference equation. I have a difference condition on the coefficients. And moreover, these coefficients, these all the terms in this expansion have the same total degree. Total degree is always 0. Because the top is going to be raised to the end, the bottom is always going to be raised to the end. And when you look at this, this preserves degree. Because every time you hop a y factor on, you pull the n down 1. And so it preserves total degree. So everything here on the top really does have the right degree. And I'll multiply it by something to the negative n. Add negative n to the total degree. And so they're all degree 0. So this guy, homogeneous, degree 0. And so that's a little similar to that algebra proof before when I looked down the vector 1, 1, 1. If I look at a monomial, it's x to the 10, y to the 11, z to the negative 3, I could label a graph, just the integral lattice, and just stick whatever coefficient here is, say 7. So if I have some expression, so then I'll go out to my graph here, say that's x, y, and z, I'll come out 10, and I'll come out here 11, and go down here 3, and at that point I'll draw 7. So I can represent these formal series as long as this actually, even if it's just a vector, I can just have a vector labeling of 3-dimensional integral lattice. At that coordinate, put the coefficient. And since it's homogeneous, I'm stuck in one homogeneous plane, so they're going to fill out a grid that looks like equilateral triangles. Delta x plus y z can be represented as a labeling of the they're not well, I guess I'll call it a graph. That's one homogeneous slice, 3-dimensional integral lattice. And I'm going to stick
It's
with
taking a lot of practice to draw that.
that. Yeah. I found a place I could print out paper that had this. I've been doing it for a while. I kept on messing up my notebooks. So if I stick this on, it's going to be the -1 homogeneous slices. It's a little easier to see. And I can at least see one of the triangles, which is right here. And this is actually a little more what we're going to be interested in. And so maybe I'll take that to be this triangle here. So that's still annihilated by the same polynomial. Multiplied by z to the -1 does not affect that. So I push forward on the x-axis and the y-axis and the z-axis, all three of them. So it would be as if I push this term forward with x, this one with y, and this one with z. And so, see, I think it should be that this guy is the sum of these two. So this is alpha, beta, gamma. Gamma's alpha, that's right. Minus alpha. But essentially, it's the downward turning triangles. The lower one is determined by the upper two. Any of the corners is determined by the other two. So that's not true for the upper triangles, just for the downward one. So I'll use this fact to help prove some identities. First identity. Z inverse delta of x is y z. It says x inverse delta of z minus y over x. I claim this is true. So, first of all, it's definitely true for negative powers of y, because neither of them has any negative powers of y, so all the terms there are 0. So here, let's see which direction is, I said y is this direction maybe. So constant y is this, I guess it's here. So at some point, which direction is negative? I guess at this, but it actually doesn't really matter, I just need zeros on one line. It actually gives me a half plane. So I should have zeros like that. And now, I'll look for a second slice of this to check. So I'll take the power of z to the -1 on both sides. Because the left side is really easy to extract the power of -1, it's just 1. So it's that times the constant term here, which is 1. And over here, I'll call this residue with respect to z. It's the formal residue. So res z x to the -1 delta z minus y x. And I'll rewrite that using the Taylor theorem. Reading the Northern property. Res z e to the negative y partial with respect to z, x to the -1 delta of z over x. And that's pretty easy also. If you take the derivative, there's no power of -1. Those are all formal derivatives. So none of those terms can contribute. So just the first term can possibly contribute. And that's also going to be equal to 1. So that's the second slice. Along z. I guess that's this direction. Now I've got this recurrence, so all those are 0. And there's 0. And that's 0 and that's 0. That guy's 0. And the next one over 0s. Same thing over here. And then you just keep going up. They're all 0. So it's proof that I just need to check 2 slices. 2 non-parallel slices. Yeah.
I'm sorry, why did you need 2 slices?
I can't go up.
Okay.
Yeah, if I had just